Today, in this session, we have four very distinguished speakers talking about known good die. And the first of them, Jan, has been the voice of reason, the voice of sanity, I think, in the market for many, many years. A lot of respect for what Jan has done. She is president and founder of Techsearch International, which has provided market research and technology trend analysis in the industry since 1987. She's co-author of How to Make IC Packages, a columnist with Printed Circuit Design and Fab, an author of numerous publications on emerging trends in semiconductor packaging and assembly. Senior member of IEEE and IEEE EPS Distinguished Lecturer. Oh gosh, the thing she has done is just amazing. Member of SEMI, SMTA, IMAPS, MEPTEC. Received an IMAPS Partnership Award in 2012, a Daniel Hughes Memorial Award in 2018, an IMAPS Fellow. And before founding Techsearch International, she served on the corporate staff of Microelectronics Computer Technology Corporation, which was the first pre-competitive research consortium. Which is pretty important because there's been many of them which have followed, and the good news is we have Jan that's tried to track all the trends and help us keep our direction straight over the years. So Jan, take it away.
Thanks so much. So welcome everyone, and welcome to the virtual world. So thanks for joining. So basically, my talk is, after 30 years, why are we still talking about known good die? So I'd like to kind of go over some of the things. We went back and looked in some of our archived reports. And back in 1993, we had done a large study on multi-chip modules. And we did a survey of the merchant MCM vendors, which was kind of interesting because the single most important barrier to MCM use at that time was the availability of affordable known good die. So it's been a topic that we've been talking about a long time. Now, at that time, the majority of the bare die sold were processed through some kind of parametric or, electrical testing. And one of the problems was there was a small but yet significant number of ICs that would pass this testing but had latent defects that didn't show up until they'd been in operation for some time. So that turned to be problematic. And the low module yield increased the cost of repair and rework, because a lot of these things at that time we had, you'll remember that people designed engineering change pads into the MCMs and all kinds of things like that. And so this was an issue. Now, many of these merchant MCM vendors, you'll remember them, Micromodule Systems. You'll remember that there was a number of these companies that no longer exist anymore. As a matter of fact, we have a slide that we call our graveyard slide, where it has the tombstones of a lot of MCM companies. But suffice it to say that this was a very big challenge for them at the time, and that's why we had so many conferences and discussions about known good die. Now, the vertically integrated companies really had an advantage because they could internally fabricate their die, test them, and then put them in a package and ship it. So there was a little bit less of an issue. But if you were a merchant company, in other words, one of those companies like the module companies I mentioned, InChip would be another one. It was very difficult, I think, to make a business when you had to guarantee this. So it was a learning experience, I think, for the industry. Now, I borrowed this slide from John Park at Cadence, who has a very nice article in Chip Scale Review. And he kind of talked about the evolution of this advanced multi-chiplet packaging technology. And I really like this because it kind of gave us some of the timelines and some of the things that have gone on. So we talked about, the multi-chip modules, more than 30 years ago. Then we moved into this era of the system in package. And system in package, as we define it, is where you bring in different die from different functions, and you put them all together in the same package, and the package has a function. And it's using, in our terms, a standard type package footprint. So those have to be good also. So you had a lot of concern about the die that come in, plus the module test. And so we see a lot of test and inspection in this area in order to guarantee that when that module, that system in package or RF module, whatever it is, goes to the company, it is going to be a good part that's put down on the board. And so there's been a lot of work in that area, and it's kind of some of the same concerns that we've had when we talked about the multi-chip modules of the past. And these are mostly being done either internally inside companies that are vertically integrated, or some that are not as vertically integrated, or they're done at OSATs. And so that model has pretty much worked itself out to a large degree. But again, having known good die is important, and having a known good package at the end of the day is essential. So the other thing that we've seen now, we've moved into this era of silicon interposers, and I want to spend a little time talking about that, because we learned a lot of lessons when we worked on those at the beginning. And then we've moved into embedded bridge, some of this high density RDL fan out, which we call fan out on substrate. We're moving into this era of 3D IC and continuing on with heterogeneous integration. And these complexities increase as we go through time. And I think that that's an important thing to really understand, is what that level of complexity is, and why it's even more important to make sure that we're assembling known good parts. So what we say is we're in this new 3D era. Now, why is this 3D era important is because we're talking about advantages to optimize system power, performance, cost, form factor. I mean, you can as NVIDIA told us on the first day of this conference in a very nice presentation, it's possible to continue scaling and make a very, very large die. But there's a lot of cost advantages that people like AMD and others have found with partitioning, die partitioning. And, you know, die partitioning is not a new idea. This was something I could remember us talking about when I was at MCC, which was more than 30 years ago. And there are many advantages of doing that die partition. So yes, you can scale, but there's some cost advantages and other advantages in terms of performance that you can achieve by doing things in parts. So some of these potential solutions, partitioning the die, one of the earliest ones was our homogeneous integration, where we did the split die to reduce the die size and improve yield at the wafer. And that was what we learned from Xilinx, and I'll talk about that a little bit. We also have a lot of heterogeneous integration going on. This is the interposers, mostly silicon interposers today, although people have discussed glass. Fan out on substrate or other multi-die packages like the chiplets, and now an increasing number of 3D stacking alternatives. Now, the heterogeneous integration, it's not a package, it's many package formats. So it could be silicon interposer. The heterogeneous integration roadmap refers to this as 2DS, which some people call 2.5D. Alternatives to this are things like Intel's EMIB and other embedded bridge solutions, or fan out on organics, which is termed 2DO in the roadmap. And then chiplets, where the substrate interconnect is really providing a communication between those components. And then the ultimate, which is what we're now going into, and it's not the first time we've looked at this, 3D structures with TSV or direct bond interconnect. So let's talk a little bit about some of the challenges that people are facing. Well, first of all, when we do heterogeneous integration, this requires typically what we see are new architectures. One of the things that I noticed in the presentation on the first day of this workshop is that NVIDIA talked about their architecture. Well, their architecture may not lend itself to being broken up like an FPGA does, but nonetheless, it takes a new architecture, co-design, the use of EDA tools that are designed for this, a lot of thermal and electrical modeling. We've talked about some of the challenges. People keep talking about these very, very, very large body sizes where they'll put this either silicon interposer or fan out on substrate to this area of something like 100 by 100, which is a little bit challenging for the board level assembly because it's going to be warpage after, you know, a warpage during the reflow, the surface mount reflow, when you put that part on the board. There's also a lot of thermal challenges, new designs with low power needed. We need some more thermal interface materials and cooling methods, and we're investigating all of these things. But one of the things that's really critically important and why we're discussing it here is the test challenges. You better have known good die or a known good die strategy. You probably need more comprehensive test content that could be run at the wafer level, and certainly new methods to probe the fine pitch bump or some test coverage without touching things or touching micro bumps or these very fine pads. So I think that going forward, we're going to continue to see a lot of work in this area. Now, we heard a great presentation, as I mentioned, on the first day opening up the workshop. And what NVIDIA told us was that this GPU, the original, had 4 HBMs with 8 high stacks plus the logic layer mounted on the silicon interposer using the TSMC CoWoS process. And then that HBM with a wide bus had 1,024 IOs, 4,000 bumps, and 55 micron bump pitch. And then it was put on a silicon interposer that was about a 34 by 43 with some fine line spaces. And their latest version, which we talked about, the A100, uses now the GPU plus as many as 6 HBMs. Now, if you figure each HBM is, and these are not exact prices, but they're just to give you an order of magnitude, say they're $200 each. Okay, say the silicon interposer is $1,000 or more dollars. This is a very expensive solution that requires really high reliability. You can't be putting not to mention the cost of the GPU, but you can't be putting a very expensive things together like this if they're not known good. Of course, NVIDIA did tell us that this thing sells for a little bit under $200,000. So probably all the more reason to have some test strategies. But anyway, it's a very, you can see the complexity, the level of complexity here, and also the more expensive solutions. This is not just test it and throw it away if it doesn't work. So if we look at some of the largest interposers that TSMC is talking about, something like 2x reticle size and even larger. Some of the discussions we've seen are like 3x reticle size, where there's room for 2 very large processors, maybe 8 HBMs and a very large area package. So there's a lot of stuff, you know, a lot more that's going to go on with this. These things are going to be very expensive. And I can well imagine that you're not going to be wanting to put down that HBM unless it's known, good, tested solution. So what did we learn from these early examples? Well, when Xilinx, the first company to start shipping back in 2012, they have many products now, but their first product was basically partitioning the die so that the large die could be fabricated into slices. And those slices, they explained, were binned. And by binning, then they could put the highest performance slices together and get the most money for those. And it provided a big advantage. Now binning, think about this. It's always explained to me in the LED, high brightness LED business, that you bin things and then you put the good ones into the lights. And then all the others that don't, you know, that kind of don't make the cut, those get to be Christmas tree lights. So you can still sell stuff and get money for it. You don't get as much money, but you get some money. You don't have to throw that away. So the idea of partitioning, binning, and, you know, selling the premium parts at a premium price, and then the lower part, the less capable parts, I would say, at a lower price, but still get revenue for it, is a major advantage to companies that can do this. So you really see the value of that. Now, we see many more ASIC designs moving into production. We've talked about the GPU and the stacked memory. And, you know, I want to talk a little bit more about the next lessons that we learned in this as well. But suffice it to say that we're seeing these applications that have expanded to network systems, AI accelerators, data centers, and servers. So this type of silicon interposer technology has tremendous growth. And by the way, the interposer is typically inspected but not tested, at least at TSMC. So another example of some lessons we learned were with AMD's Fiji, because this was one of the first examples of putting an HBM stack with a GPU. And this was for the first product was for the graphics market. And there were 4 HBMs stacked, each containing the DRAMs plus the logic controller die, mounted on this very large silicon interposer. Now, one of the things that, that AMD talked about when they introduced this, and I remember when Brian Black presented some of these slides, he would talk about the test strategy and how this was very important to the success. And they did their wafer sort, their binning, they did the first assembly, they did some partial assembly and then final test, partial test assembly, more assembly, and final test. So you can see that throughout this, a lot of testing strategies, and a lot of work went into this. And I like to think of this as an incredible engineering feat to put this all together at the time. And they worked with both Amkor and ASC. These slides happen to be from an ASC and AMD presentation. But tremendous learning experience that I think has given them the opportunities as they've gone into some of the next things that they introduced and continue to introduce. So you can see that the test strategy became very, very important. And by the way, those HBMs, they need to be good when they come in. You can't be reworking them. You can't be throwing the whole thing away. It's much too expensive. Now, Samsung has their roadmap introduction where they talked about the silicon interposers. They're introducing some of their RDL interposers, a lot of their multi-chip packages, and then they're introducing their multi-die 3D. But Samsung's very interesting because they have some advantages in the fact that they are one of the suppliers of HBM, so they have their own internal production. So that gives them an advantage over, say, other companies because they're the ones that make the HBM, so that they could, really guarantee for their products that HBM would be good. But let's talk a little bit more about HBM. So the HBM, typically we're stacking the die with TSVs. You want to have these TSVs and micro bumps well joined, well aligned micro bumps. That's the way they're done today. You can't have any delamination with the underfills. So you're going to be testing these things. There's a lot of redundancy built into this stack. There's a lot of built-in self-test. And of course, obviously we have built-in self-test and everything, but built-in self-test has been critical to a lot of these applications. But redundancy is very, very important in this development, in this technology development. And so when the customer gets this thing has been completely tested. I understand it has been burned in. And so it's a known good stack. And at the price they're charging, it sure better be. So now there's a lot of suppliers for this. We have Samsung, SK Hynix, Micron bringing theirs on. Renaissance has a low latency HBM. So there's a lot of these out there, and we're going to continue to see this type of technology grow. We already have HBM2, HBM2E, and we're going to have HBM3 in the next couple of years. Now, another technology that's being used increasingly with HBM is our fan-out on substrate technology. This has been introduced back in 2016 with a high silicon network switched by ASC as a chip first. And the chip last is also being moved into production. This allows you to have the RDL with 2 micron line in space, up to 3 RDLs plus a UBM. And we also have what TSMC first introduced as their fan-out on substrate. And their basically the first product that they introduced was from MediaTek with a network switch. And that was also a split die product. Then Amkor, these are both, the first introductions, as I mentioned, were chip first, Amcor's substrate SWIFT technology is a chip last, allowing you to have known good parts and assembling this as a chip last solution. So for some people, that's more attractive depending on what you're assembling. And so that's an alternative. And that's being, what we're seeing is a lot of people look at using this with an HBM. Now, the EMIB technology is very interesting. And so we want to talk about where known good die is really important in this one. If you look at this structure, the idea is you're embedding a bridge, a small silicon bridge into the packaged substrate, into the substrate. So there's no TSVs here, but this packaged substrate is this embedding is being done by the supplier. So what has to happen is Intel is going to fab their bridge. They're going to send that bridge over to the substrate suppliers. So if you don't send the substrate supplier a known good bridge, the substrate supplier embeds this technology, the substrate supplier's yield is very, very low. So because the embedding process has some level of loss in it to begin with, just as the nature of the process. But if you're not embedding good die, and certainly after you embed this technology, you're not going to be doing any repair on it. And so it becomes very important for Intel to be working on how to make sure that they're supplying known good bridges for the substrate guys to embed. And obviously there are big advantages of this. And this has very high, you know, the volumes today are where we have used the AI accelerator with the FPGA technology that when Intel purchased Altera and incorporated that into their systems. Now in the future, we expect to see this play a greater role and we expect to see it in things like the server systems in a couple of years. But let's talk about 3D integration, because this is really what we're seeing as, it's kind of like the holy grail, if you will. And so we've got HBM in production at Samsung and SK Hynix. We know that Micron is sampling. I don't have an update on exactly where those are right now. I would expect those to be in production in the near future. Another type of 3D integration is the Intel Foveros process, where today it's using a micro bump. But again, that's a structure where you want everything to be known good before you assemble it all together. TSMC's SOIC and wafer-on-wafer technologies, where you're either putting a chip on the wafer to form that, or you're putting two wafers together. And you really would have to have very mature technology. Now, TSMC has not informed us of exactly how they determine that they've got a known good structure, but I would imagine they're spending a lot of time figuring that out. Maybe someone in the audience knows. But anyway, the new forms of 3D stacking that we're seeing are these die-to-wafer attach and wafer-to-wafer attach. Now, think about it. If you're doing these things with no bumps, that means that you'd have just pads there. So if you're going to put together a structure using these hybrid bonding or direct bond interconnect technologies, I would imagine that you can't have a probe pad, a pad that's has a probe mark on it, to be doing that assembly. So I think it's going to be fairly challenging to figure out how these things are actually going to be, you know, determined that they're known good, and what level we'll be going to on the testing to get that. And I'm sure that that's something that everybody's spending a lot of time working on. Let's look a little bit more at what this 3D technology is with the Intel Foveros. This is where we're stacking basically die on an active interposer as opposed to a passive interposer, which is what CoWoS would be. So the active interposer, and I think Bob Patty alluded to this, is just like a really large die because it's got active circuitry in it, but it is done on older technology. So if you think of it, you'd want to make sure that that is a good structure, and the things that you stack on it are good structures, because I have not heard anybody talk about doing a rework step for this. So you really want to make sure that everything you're pulling together. So I think there's a lot of work going on in terms of how we make sure that we're assembling these known good parts. because I think you're going to want to catch that at the very early stage in order to improve your yield and basically make sure that your revenue stream is what you would expect it to be. Now, as I mentioned, TSMC is introducing their SOIC technology. They've talked about this in many places now. The first commercial products we expect to see next year. We know that there's some design work going on now, and we expect to see commercial products with up to 10 chiplets in 2 to 3 years. And that means that each one of those chiplets is going to have to be somewhat certified as good in order for you to assemble that. And we're talking about very advanced nodes, technology nodes, and other things. And we also see a lot of discussion about putting this, say, next to an HBM on CoWoS or something like that, or on an RDL structure. So this will be very challenging moving forward to how we'll, and remember, there's no bump on this, so you can't probe a bumped part. You're probing, if you're probing, you'd be probing the pad. Now, one of the things that's been very interesting that's introduced recently is Samsung has announced their 3D heterogeneous integration, where they're going to stack SRAM and logic together. With the first products are going to be micro bumps, but I'm understanding that in the future you'll probably see hybrid bonding. Now, we're going to hear a lot more about this at the IWLPC next month, when we hear the keynote presentation and some other presentations as well. But we're going to hear a lot of discussion about this. And what I want to tell you right now is that, you know, it's not the first time people have talked about stacking memory and logic. Back almost 10 years ago or more, we had a lot of discussion about stacking DRAM and logic. But the difficulty at that time was a couple. One was the thermal issues with the hotspots on the logic heating up the DRAM past its duty cycle. However, this is an SRAM stack, so this is a little bit different in that respect. And also, we're also looking at this as a structure with perhaps some different test strategies and things that we hope to hear about later. But one of the reasons that people did not go with this earlier in production was also the fact that back in the day, we expected to see a 3D IC move into the mobile phones. And Qualcomm, long years ago, had almost qualified something to go into production. But there were a lot of concerns and issues, a lot of concerns with the memory. How could you change memory suppliers? What if your memory wasn't good? Could you test the memory well enough? And so that's why you have so much package on package, because you'd have a memory package separately from a logic package and stacked together. And so what we ended up with a POP package is something where you could have those packages tested and the DRAM come in fully tested and stacked. And so this really will bring us into a new era if we can put this together and solve the test problems, solve the known good die problems, and be able to move this into production. It's really a breakthrough to do this, as well as some of the other technologies. So I think that we've really moved in our industry forward in a lot of ways. We've obviously done a lot to gain the possibility of us being able to move something like this into production, because it's as everyone has always known, it has tremendous advantages. So I hope we hear more about in the next few weeks or so how Samsung has solved some of these test issues. So in summary, I'd kind of like to say that I think that known good die is still required. I don't think we're going to get away from that. I think that what we've been helped with a lot is built-in self-test and a lot of redundancy built in. I think that we've seen a lot of progress in this area. And we need a known good substrate. We've seen a lot of inspection used for this, with AOI for the interposers. I think we're still going to see a lot more inspection needed moving forward. People kind of assume that there's a known good interconnect, but what we have seen people talk about is having to use X-ray systems like the XVXR system in production to make sure that those interconnects are good. So a lot more work on that. And I think we need some more comprehensive test content that can be run at the wafer level if we're going to do what TSMC and others are proposing, where we have their like SOIC, where we're stacking things together with hybrid bonding or direct bond interconnect. And then we're going to need new methods if we can't probe the fine pitch bumps or some test coverage without bumps to handle that. So I think that we've heard a lot during this conference, and I expect we're going to hear more moving forward. And I hope that some of the future presentations will talk about these areas. So I'd like to thank you very much. And I think I've left enough time for questions, hopefully.
Yeah, I think we have time for a few questions, and some good ones have come in. Let's see. The first one is an interesting one. First one I want to pick anyway. And it's the title of your paper says, why are we still talking about known good die 30 years later? Where did we miss the boat? Why are we still talking about this?
Well, I think that we haven't missed the boat. I think that we've made steady progress in the last 30 years. But I think that the idea that you don't have to have known good stacks. I mean, if you talk to one of the customers for HBM and tell them, well, this is probably good, and we're going to charge you this big amount of money for this stack of stuff, I don't think they're going to go for that. So what I'm trying to say is that we can't get away from the fact that we've got to provide a known good part to assemble. And the level of complexity is increased. But what I also want to say is it's not like the industry hasn't been working on these issues, that we've made a lot of progress in things like redundancy in those memory stacks, built-in self-test, have really helped us a lot. Now, some of the things we worked on didn't work out. I remember when TL worked on a burn-in system that never went into production. They spent a lot of money on it. And there's a lot of paths we've gone down that have not worked. But there are a lot of things that have worked. And I think that also one of the big things that I think has happened in the industry, and I think it's been pointed out in some of the examples with Xilinx and AMD early on, is that partnering and working with the supply chain, including everything from test and assembly on up.
Got it. So there's a few questions around basically how we decide when a multi-chip integration can be done. For example, you know, it's a high price tag associated with 2.5D and 3D. Has anyone done the math to determine the minimum chip price where it makes sense to consider this, and what the trade-off is?
Well, yes, there's been a lot of work done in that area. First of all, you see often people do an assessment of what it would be if you did a monolithic die and the cost of that versus what you would do if you did a chip partition. And many times, you know, there's some cases where if you could do a monolithic die, maybe you would want to do that. But because of basically, and I remember a presentation at last year's SEMICON Taiwan where MediaTek showed the examples of the die yield, the improved die yield when you partition things. And the die yield is so great that you could actually justify using an interposer when you improve the yield at the wafer level that much. So it depends on your product. I mean, if you can assemble parts and you can do a final test, and if it doesn't work, just throw it away, then that's fine. So it really depends on what it depends on what you're trying to do. Just like the binning of the LEDs. You know, if it's it's a low valued part, you can put it over here to the side. I mean, you know, sure, you don't want to, but I mean, if you look at the level of complexity moving forward, I think that, you know.
We'll get there. I mean, Christmas lights is a good example. Where won't we get? You know, in a pie in the sky type thing, what won't happen in terms of 3D integration? Will RF be stacked? Will millimeter wave be stacked? Power amps, PMIC devices? Do you see any constraints that we won't
Well,
likely
I think
overcome?
I think you certainly need to be careful what you're stacking. I mean, I know there's a number of examples of, I mean, look, we've been stacking stuff for a long time. Look at Sony's image sensors, how many there are out there. Look at, but you know, that's a different, the more complex the item is, and the higher the value add when you start stacking it, the better your test strategy has to be, and the better, the more important the guarantee of being known good at the end of the day. Now, I mean, if you're a foundry, you can probably just run some more of these things and assemble them in the back and eat the yield. But if you're an OSAT doing an assembly, you probably would have, you wouldn't be able to do that.
So what about vertical integration going south to the interposer? You made an interesting comment that the interposers are visually inspected today, not tested. Interposers in the future are going to be active, and they're going to have
In
passive
that case,
devices.
you're going to have to test them.
What's
Because passive interposer, TSMC, in many questions that I've asked in conferences, has indicated that they do not test them, they simply inspect them. Now, I don't know about everybody else, but that's an answer that I got from a question. Now, moving forward, if it's an active interposer, as you know, Bob Patty mentioned in his presentation yesterday, it's like a large die.
Yeah.
So you're going to have to do some level of testing, at, I would assume. I mean, I've never asked that question to one of the people about the Foveros technology, but I would assume that you have to treat it as you would a large die.
I would assume the same. I'm just curious when we're going to have to confront that, peel that onion. I suspect it's sooner rather than later, but we'll see. With the emerging chiplet solutions from Intel, Samsung, NVIDIA creating challenges for the OSATs, will we see a return to more vertical integration? It seems like, you know, pulling all these pieces together, only the vertical model can really manage all the variables that need to be done here. Do you see that?
Well, that's an interesting topic, and that is the topic that we're going to discuss in the IMAPS panel discussion coming up next month as well, where we talk about who's driving the bus for the ecosystem as we go into these technologies. And you know, it's really, if you're the foundry, you know, if you're TSMC, if you're Samsung, you have some advantages because of some of the things that you have inherent there. If you're an OSAT, but they can't do everything, so there has to be a partnership with an OSAT as well. So I really think what the difference, what we're really seeing now is people really understanding the importance of collaboration and working together more than ever, as opposed to 30 years ago when I first came in, you know, first was in this industry and doing all these discussions, everything seemed to be done in a silo. And there was a real, I thought, lack of communication. And I think that the industry has really made great strides over the years in improving that level of communication to develop these complex systems. And I don't see that changing moving forward. I don't know if that answers your question, but.
Okay. So Bob Patty spoke yesterday about design for redundancy, resiliency, and the like. Obviously, that's one way of confronting this known good die topic. How do we promote that better?
Well, I think conferences like this will provide a great platform to discuss that and make sure that people understand, you know, the needs for it and the advantages of it. Obviously, and you know, the more we can discuss that and bring in the EDA folks into the discussion, because everything is about, you know, optimization and communication up front, if you will.
So we can do that certainly in the silicon space. The interconnect space is perhaps a little more difficult to do this resiliency, redundancy, and certainly the repairing of things. Do you see a time when we will be doing die level repair, or do you, well, I have a related question after that.
Well, die level repair, we have built-in self-test, and I think you're going to see more of that happening if that's what you're referring to. I mean, clearly there are advantages of it. Obviously,
Sorry, I meant more die level swap out at the interposer level.
not sure about that. I'd have to ask some of our friends that do that assembly.
Okay, so one of the assembly techniques, or there are some new assembly techniques, hybrid and copper diffusion bonding techniques. Do you see those catching on and being a new challenge for us?
They are very challenging, but they are very, if you listen to some of the presentations by the people that are offering those, TSMC's SOIC, the Intel Foveros, even though it has micro bumps today, it will probably eventually have the hybrid bonding. The tremendous advantages in terms of performance, in terms of signal integrity, power savings and things that I have seen presented are very compelling. And so while you're not going to shift everything over into direct bond interconnect or hybrid bonding, certainly there's some things that are going to move that way. We know that the memory people, for example, that one of the issues with the HBM is the throughput to stack those. And we know that many of these companies are very much looking at the possibility of doing a hybrid bond to improve the throughput. Now, there's a lot of challenges with that, but you know, the memory would be a large space. That would be a very high volume application. We already have it in image sensors, both Samsung and Sony. We have the flash memory from YMTC that's supposed to be shipping. We have a lot of things that are moving in that direction, but no, will it be everything? No. People need to get away from this idea that once you get one of these technologies, you put everything, you use it for everything. It's not a one tool fits all.
I was surprised that you touched on wafer stacking in your talk. I hadn't personally caught that had caught on. I mean, are we even doing wafer stacking on the HBMs?
No, we're not doing wafer-to-wafer stacking today, but obviously people are looking at you know, possibilities for things. And we are doing it in flash. I mean, that's what the YMTC
Sure.
is, the controller layer and the memory layers and put them together. And I think certainly TSMC has presented that with a very mature technology, that you could do some wafer-to-wafer stacking. And also, I'll remind you that there's some wafer-to-wafer stacking in what Samsung has introduced on their integrated chip capacitor, I believe, if I'm not mistaken, from the ECTC paper they presented.
I just see the yield pile up problem being fairly significant. I would think you need incredibly high yield even with a mature process.
Technology. Yes, you need a mature technology, and that's certainly what people have said when they've talked about and presented it. But again, it has tremendous advantages. So I think that the industry is, you know, let's look and see how the wafer-to-wafer stacking goes in the flash memory area, and I think we'll learn a lot from that.
Yeah, but flash memory is more vertical stacking than die-on-die stacking, so a little different world.
Well, we'll just, yeah, we'll see what happens.
Okay, I think on that note, we ought to thank Jan for an excellent paper and good discussion.
I'd like to thank all the speakers, and I'd like to thank everybody who's attended. I think we've had great participation, a lot of interaction, some really great questions. Also need to thank our sponsors who've made this event possible. ASC, Advantest, GelPak, Mullbauer, Amcor, and Microcircuit Laboratories. Our diamond sponsor is ASC. They provide OSAT and EMS services, the whole range from design, assembly, test, materials, components, and logistics. And then we also need to thank Advantest with over 30,000 installed ATE systems worldwide, deep expertise, a large workforce, and been in the measurement arena for over 60 years. So thank you, Advantest. Also, thank you to GelPak, whose goal is to protect the world's valuable devices both in manufacturing and in process and in storage and in transport. So Gelpack, we appreciate your support. And lastly, we thank Mulbauer, whose specialty is factory automation and data to drive the manufacturing process. So we thank Mulbauer for their support. Once again, I thank everybody for attending. I hope everybody found this a worthwhile and informative event. Please send us your feedback. I'd love to hear it and hope to see you at a future MEPTEC or event and in next edition of Known Good Die Workshop next year. So I thank everybody and I wish you a good remainder of your day. Thank you.